today is our problem session 11, perhaps the last of the, it is the last problem session, okay, and this problem shall be on 2-port synthesis. The first problem we do is 12.2. 12.2 gives two networks and says show that the residue condition holds for the networks shown in the figure. The first figure is 1 ohm, then you have a 1 and 2 farad and half farad capacitor. It says simply that show that the residue condition is valid. Okay. Now, residue condition can be with regard to either Z parameters or Y parameters, and obviously if one is clever, one should not try to find Z parameters of this network, one should only try to find the Y parameters, and Y parameters are obvious. Okay. So, Y11 is 1 plus the whole thing comes in parallel. So, 2s plus 1 over s, agreed? If this is shorted, 2s 1 over s, y12 is equal to minus 2s minus 1 over s, and y22 is equal to s by 2 plus 2s plus 1 over s, which is equal to 5s by 2, 2 and a half, 5s by 2 plus 1 over s. That's right. If this is shorted, these two capacitors come in parallel. So, s by 2 and 2s, and I have combined them into 5s by 2. Okay. Now, the pole at infinity, there are two poles, one is at infinity and the other is at the origin. For the pole at infinity, s equal to infinity, k11 is 2, k22 is 5 by 2, agreed, and k12 is minus 2, and therefore k11 k22 minus k12 squared is equal to 5 minus 4, which is equal to 1, that is greater than 0. So, the residue condition is indeed valid. For the pole at the origin, k11 is 1, k22 is 1, and k12 is also equal to minus 1. Therefore, k11 k22 minus k12 squared is equal to 0. Again, residue condition is valid. Okay. The B part. Any question on this? The B part is slightly unusual. One has to think a little about it. The network is this, and you see that this is not a pure LC or RL or RC. Residue condition validity as I said happens only in 2 element kind networks. It is not necessarily valid in 3 element kind network. This is an RLC network, but still the question says show that the residue condition is valid. Therefore, you shall have to find the poles of the 3 parameters, the residues there, and show that the residue condition is valid. Is the point clear? This is not an RC, RL or LC network. This is an RLC, and it says that the residue conditions are valid. You have to show them. So,
previous one was RLC.
Yes, that is correct. Previous one was also RLC, but fortunately the poles were only on the j omega axis. Okay, s equal to infinity and s equal to 0.
So also the RLC circuit may satisfy residue.
May satisfy, may not also satisfy. But let me mention to you, just mention, it's not very important at this stage, that in an RLC network, if there are poles on the j omega axis, then residue conditions must be satisfied. Okay? Poles on the j omega axis, residue conditions have to be satisfied. This is not true for any other kind of pole. Okay. Now, for this part of the network, which parameters would you like to find out? Z or Y? Y or Z? Okay, either of them is good enough, but
so
how?
we can convert this pi into T and then take the Z.
Okay, we can convert this pi into a T and then add 1 ohm to Z11, alright, or we could convert this T into a pi and find Y parameters. Okay, either of these two procedures would be okay. Do not try to find from the definition, that is finding Z11, Z22 and so on. This will be messy, particularly in finding Z12 you shall have to write node equations or loop equations. There is no other way. Suppose we take the first alternative, that is we first find out the Z parameters of this network. I prefer not to memorize any formula except the conversion of parameters, okay, and that is very simple. So, for this network Y11 is S by 2 plus 1 over 3S, alright, is that okay? Y12 is minus 1 over 3S and Y22 is equal to 1 plus 1 over 3S. Therefore, del Y, the determinant Y, is the product of these two, S by 2 plus 1 over 3S multiplied by 1 plus 1 over 3S minus 1 by 9 S squared. Okay, and if you simplify this, I have done so, I will skip some of the algebra. If you simplify this, del Y is equal to S by 2 plus 1/6 plus 1 over 3S. This is my result. Therefore, I find Z11 as equal to, you must remember this, Y22, that means Y22 by del Y. So, it is equal to 1 plus 1 over 3S divided by S by 2 plus 1/6 plus 1 over 3S, and this simplifies to 6S plus 2 divided by 3S squared plus S plus 2. I hope I am right. That is my calculation. In a similar manner, you can find out Z22 as Y11 by del Y. It is not a symmetrical network, unfortunately. So, you will have to find all of them. This comes out as 3S squared plus 2 divided by 3S squared plus S plus 2. Then Z12 is, pardon me? Oh, it is not visible, okay. Let me write. Z22 is equal to 3S squared plus 2 divided by 3S squared plus S plus 2. Z12 is minus Y21 by del Y, and this my calculation gives 2 divided by 3S squared plus S plus 2. Let me also write the expression for Z11. This is 6S plus 2 divided by 3S squared plus S plus 2. You notice that the three parameters are the same poles. Where are these poles? Poles are at 3S squared plus S plus 2 equal to 0, and if you solve this quadratic, my solution is that poles are at S equal to minus 1 plus minus j square root 23 divided by 6. Not a happy situation, but not too bad either. Okay, there are two poles two complex conjugate poles. You will have to find the residues at both the poles. Okay. Let us find the residue of Z11, let us say, residue Z11 at S equal to, pardon me?
Add 1 ohm resistance.
Okay, okay. So for the total circuit Z11 equal to 1 plus 6s plus 2 divided by 3s square plus s plus 2. Alright, Z22 remains the same, that is 3s square plus 2 divided by 3s square plus s plus 2, and Z12 is equal to 2 divided by 3s square plus s plus 2. Now this addition of 1, does it change the poles? No. Does it change the residue?
Yes, I do.
How do you know?
So multiplying the pole.
It does not change the residue. Why not? Let me tell you why not. Okay. Residue of Z11 at S equal to minus 1 plus j root 23 divided by 6. This would be S then minus 6 minus 1 plus j root 23 multiplied by Z11 at S equal to minus 1 plus j root 23 divided by 6. When this factor multiplies this constant 1 and you put S equal to this, obviously that leads to 0. So it does not change the residue. Is the point clear? Okay. So all we have to do is 6s plus 2 divided by, what shall you be left here with? If you multiply by this factor, obviously the other factor
2j root 23.
S minus 1 minus j root 23 divided by 6. This is what shall remain?
Twice of j imaginary part. So plus 11. So now we are adding the conjugate.
Plus, why plus? Just a minute. It is the conjugate. You see, the denominator has two poles. One is S minus S1 multiplied by S minus S1 star. Okay? And I have taken here S minus S1 star. Have I made a mistake? And this would be equal to S at this point minus 1 plus j root 23 divided by 6. I have made a mistake. You see, the factor here was 3s square plus s plus 2. Obviously, this would be s minus s1, s minus s1 star. That factor 3 has to be there. Isn't that right? No? Okay. So the factor 3 has to be there. I don't know if I had, yes, I had taken that into account, fortunately. And if you substitute this, it's not too bad.
1 plus j plus root 23 by j root 23.
That means 1 minus j by root 23.
Yes.
Is that right? That means this is equal to K11. If you simplify this, this is what the result is. I hope I am right. Yes. Similarly, now you have to find out K22, which I didn't have the patience to. I hope you shall have the patience to find out these values. And it's not too bad because things cancel and you get nice things like, it's not very nice but not too bad, okay. Square root 23, let it remain square root 23. Ultimately you can show that the residue condition is valid. Okay, any question? It's a bit of algebra but one has to do it. We next go to 12.4. Pardon me? Similarly, you have to calculate for the other poles. Yeah. We next take up 12.4. It says for the networks in the figure, show that the driving point impedances Z in are equal to R when ZA ZB equal to R squared. you have to show, let us take the A network. R ZA and ZB R. You have to show, and this voltage is V2, you have to show that this impedance is equal to R, show when ZA ZB equals to R squared. Now when terminated by R, the input impedance is R. Can we call this a constant resistance network? No. No, it is not symmetrical. Constant resistance network is one in which it does not matter which way you terminate. So this is not a constant resistance network, but it is an interesting network that the input impedance is the same as the terminating, at least in one direction. Okay, and the showing of this is not difficult at all. Input impedance Z in is R ZA divided by R plus ZA plus R ZB, two parallel combinations put in series, R plus ZB. Therefore this is R multiplied by R plus ZA, R plus ZB, and in the numerator you have ZA R plus ZB plus ZB R plus ZA. That is equal to R plus ZA R plus ZB, and in the numerator you have ZA ZB, which is R squared. Similarly ZB ZA, that is R squared. So 2R squared plus R ZA plus ZB. Is that okay? ZA ZB, if ZA ZB equal to R squared, then this step follows. Okay? And you see that the denominator is the same, R squared plus ZA ZB, which is also R squared, plus R multiplied by ZA plus ZB. So this is simply equal to R. I am skipping an algebraic step. Similarly, you can show about the other. Similarly, but they are not constant resistance networks because they are not symmetrical. Nevertheless, these networks are of interest. Our next problem would be 12.7. 12.6 we already did in one of the problem sessions, if you recall. I think on LC networks, LC network synthesis. Yeah. 12.7. Here is a constant resistance network. It is a constant resistance bridged T circuit, and the circuit is like this. R, you have a ZB and a ZA. This is indeed a constant resistance circuit and it says that if ZA ZB equal to 1, that means you put R equal to 1 and ZA ZB equal to 1, you have to show that under this condition you have to show that V2 by V1 is equal to 1 by 1 plus ZA. Okay, this is what is to be demonstrated. Pardon me? I didn't understand your question. Oh, circuit, this is the circuit. Draw the circuit.
So how do you know that ZA ZB is equal to R square?
How do I know? Well, it's given. Show that if ZA ZB equal to 1.
That is equal to 1, not R square.
Well, if it is R square, then the input impedance is R. One can show. Okay, let's show that first.
Yes, sir.
All right. So if you terminate by R, since this is a symmetrical network, it will be true for the other also. What is the input impedance? That resistance or terminating resistance also. That is the definition of constant resistance network. That if terminated by R, yeah, the internal resistances are also R. Yeah.
So that means that for a different value of R, for instance, we were to terminate to a different resistance, would
Correct.
it be a CRN?
Yes, it would be. If it is R1 and R1,
Yes, sir.
then the condition to be satisfied is Z as ZB equal to R1 square. Then if you terminate by R1, the input impedance would be equal to R1.
Why we terminate by R?
One at a time, yes.
Suppose you were to terminate by R2.
Then it would not be a constant, no. Then the input impedance is would not be R2.
So that means that whenever it is a part, the resistance is a part of the network itself, then you have to terminate only by that to get the...
In this particular network, yes. There may be others in which the resistance is not part of the network. Yeah. Any other question?
For instance, in this 12.4 also,
Yes.
we had R used within the network itself.
Correct, correct. R is used in the network itself. Quite correct. What was your question? Okay.
In the 12.4,
Yeah,
for proving the second circuit, we
Correct.
are going to terminate by R.
no more termination. Termination is already there. You have to show that the input impedance for 12.4 second circuit, you have to show that the input impedance is R.
And for A part, the termination is ZF parallel R or simply R. So because
There is no other termination. This is the network.
So it doesn't matter. Both of these are not constant resistance.
They are not constant resistance. So termination doesn't matter. But they are used in synthesis. Both of these networks. You replace R by a second network of this type and terminate that in R. You see what I mean?
Yes, sir.
So you can make cascades of this.
No, sir.
That is the
Again, we need to have that network in parallel with ZA also.
right. You see, you use another network R ZA1 then ZB1 such that ZA1 and ZB1 multiplied again gives R square. Okay, can we go back to this question? How do you show, what procedure do you follow to show that Zin equal to R1? What procedure?
T into pi. Convert T
You convert this T into pi and then combine with this ZA, then you write the input impedance. Is that the only method? Anything else?
So when we assumed R equal to 1,
We didn't assume, it's given.
so it's given Z is Z equal to 1, it's not given Z is Z equal to R square.
that we have
Oh.
not proved.
That is R equal to what? We have not proved yet.
So it's not even stated that way.
It has not been stated that way. But this is a property of the network that if it is terminated in R1, then the input impedance is R1. And the condition for that is that ZA ZB equal to R1 squared, which fits in here, which only means that R is equal to 1. This can be shown. Okay, I will skip that part. Shall I?
Yes.
Is there any other method to show this, that the input impedance is R? Instead of converting this T into a pi, can you think
so
of
by
some?
assuming by the symmetry of the circuit, if we put R1 on the open port,
Oh, no. What I was saying is, you could also consider this. You could also consider this as a pi and then as ZB. You could do that. Convert this into a T. What you said, convert this T into a pi and combine with ZA. I could also convert this pi into a T and combine with ZB. So, whatever method you follow. Pardon me?
so one more resistance.
There is no more resistance.
Across that
Okay, you have to ultimately connect this. Ultimately, you have to connect this resistance. But let's go to the transfer function problem. You have to show that if 1 ZB ZA and this is terminated in 1 ohm, this is V2 and this is V1. The problem is to show ZA ZB is equal to 1. Problem is to show that V2 by V1 is 1 by, what is it? 1 plus ZA. Okay, you can do it in the same manner that you did. You could convert this into a pi, combine with another pi, then find out the transfer function and so on. To bring variety into experience, let us do it in a slightly different manner. You remember I pointed out that if there is a voltage source connected to two networks, you can think of this as a two networks in parallel, okay? Then you could split the voltage source. That is, you could split this connection and connect a voltage source V1 to each network. Let us see if that gives us any simplification. You understand what I mean? If I disconnect it here and then connect a V1 here and connect a V1 here, it is not changing matters, remains identical, but it solves the network almost by inspection. No calculation is needed. Look at the simplicity. You have a V1 1 ZB okay, then you have another V1 which is simply connected in series with ZA, and the whole thing is connected here and connected to a 1 ohm resistance, and this is V2. All right?
Sure, sir.
Yeah.
So can you have a circuit like this with two sources on either side and 1 ohm resistance in the middle, shunt 1 ohm resistance in the middle?
No, I didn't follow.
So,
Two sources.
so can I draw the circuit? So
Yes.
there is one source V1,
Yeah.
ZA in series, then 1 ohm in 1 ohm shunt,
Yeah.
1 ohm series, ZB shunt, 1 ohm series, and
That's what I did, isn't it? 1 ohm, then 1 ohm
yes, sir, yes.
ZB. That's what I did, exactly the same thing. But I have to make sure that the potential of these 2 points are the same. That's all that I require, right? Potential is V1. Now you see, as far as this network is concerned, it can be solved almost by inspection, because if we apply Thevenin's theorem here, then the equivalent would be V1 ZB divided by ZB plus 1, equivalent voltage source, and the equivalent internal impedance would be 1 into ZB divided by 1 plus ZB. Okay, so I can draw this by inspection. V1 ZB by ZB plus 1 plus minus, then this impedance is ZB by ZB plus 1, then you have a 1 ohm, and the other one is V1 ZA, and this is connected here, the whole thing is connected to a 1 ohm, and this voltage is V2. Okay, all that you have to do now is to write one node equation, that is V2 by 1, this current, plus V2 minus V1 by ZA. This is the current in this direction, and the current in this direction would be V2 minus V1 ZB divided by ZB plus 1 divided by ZB by ZB plus 1 equal to 0. That's all. No conversion, no formula, nothing to remember. It is just one application of Thevenin's theorem. And all that you have to do now is to simplify this to find V2 by Z. And you can very easily show that under the condition that ZA ZB equal to 1, this is exactly 1 by 1 plus ZA. Any question? These are some of the tricks that one exercises. This, you will not get this in a textbook, but it's common sense. I have also cautioned you that had the input been a current source, the procedure would not have been valid. Have I or have I not? Current source cannot be split like this. Number 2, if this voltage source had a non-zero internal impedance, then also we couldn't do this. It's only in the case of an ideal voltage source that you can do this, that you can split, not otherwise. Okay, part B. Part B says synthesize ZA and ZB if V2 by V1 is equal to S squared plus 3S plus 2 divided by S cubed plus 4S squared plus 5S plus 2. Alright, all that you have to do is to equate this to 1 by 1 plus ZA, and then find out ZA. If you do carry out the algebra, very surprisingly ZA turns out to be equal to S. Can you tell me why? Can you tell me why this is S? If this is S, then obviously the transfer function will be 1 by 1 plus S.
S square plus 3S plus 2 cancels.
That is correct. These two polynomials are not primes with respect to each other. In fact, it can be shown that this is 1 by S plus 1. If ZA is S, then what is ZB? Obviously 1 by S. And the synthesis is complete. This transfer function is a degenerate transfer function. That is why it is so. Our next problem is 12.9. Taking only non-trivial problems. Most of the others are trivial. 12.9 says synthesize the two-port NA. Now it is not singly terminated, it is doubly terminated. It is terminated on both sides. This is V2 and there is a voltage source Vg in series with a resistance. It is not a pure voltage source, it is not an ideal voltage source. It has a resistance. That means there is termination here also. Such a network is called a doubly terminated two-port. We have not learned this synthesis. Despite that, the question asks synthesize Na with termination resistors R2 equal to 4 ohm and R1 equal to 1 ohm to give V2 by Vg as equal to 12S squared divided by 15S squared plus 7S plus 2. This is what is specified. You are required to find Na. Alright, there are two terminations. The first thing, any suggestion as to how to proceed? Those nice procedures, Z21, you divide by the odd part or even part, that doesn't hold, because you have a termination on both sides.
So we can find the input resistance and then.
We can find the input resistance here. How does that help?
So then we can change this terminal to so divide Vg into R1 and that will.
So, how does that find?
Then we can apply that.
We can convert the voltage source into a current source, take the 1 ohm and add it with the 4 ohm over there and make it 5 ohms and then.
Oh no! You mean I convert this into a current source and transfer this resistance over the network Na? I am not allowed to jump. No. That will destroy the complete network. You can't ignore Na. The effect of Na is an insertion network. Any other suggestion?
Should we convert the Vg and R into its Norton equivalent?
Why aren't you thinking in terms of Na? What is the possible structure of Na? What is the possible structure? How many zeros are there? Transmission zeros, 2, and both of them are at the origin. So it must be a very simple network. Can you guess what the network would be? A series capacitor and a shunt inductor. That's it. A series capacitor and a shunt inductor. This is C, this is L.
So this is 8 and 12.
Can we have it the other way around? Can we have L here and C on the other side? Why not? Can we have like this? because we don't have an ideal voltage source or an ideal current source, we have a resistance here. So there is no reason why this should not work. Alright, so either of these two networks would work. Let's choose one of them
So
and
there
then
is no
see.
set method like for single resistance termination we have.
Single resistance termination we have because there is a pure voltage source or pure current
So
source.
similarly don't we have for the other?
No, here both of them will work because there is a resistance here.
So for one side termination we calculated Z12.
Correct.
So it's just
Oh, for both sides,
yes sir.
yes, that's what we will do. We will find out the parameters, but in a heuristic manner. There is no set rules for this. Let's see what our Vg, and then we have 1 ohm. Let's take this C L.
So we are given V2 by Vg, we are not given the V2 by the voltage input at the port 1.
It doesn't matter. I have to calculate V2 by
Can we
Vg.
directly guess that network is LNC?
Oh yes, of course. 2 transmission zeros at the origin. There is no other way. These are the only 2 ways. So this is V2, and V2 by Vg is given as 12s squared divided by 15s squared plus 7s plus 2. Okay, one step is done, that we have guessed the structure correctly, hopefully. The next step is to find the values. One of the things is simply write V2 by Vg. It's a simple enough network, isn't it? 4SL divided by 4SL divided by 4 plus SL, 4SL divided by 4 plus SL plus 1 plus 1 over SC. Agreed? Simplify this. Is this point clear? This impedance divided by the sum of the two impedances, a potential division, and then equate the coefficients. You will get LNC. This is the simplest method. You can do it by any other methods also, but this is the simplest one. This is the simplest one because it is simply a potential division. You didn't have to write loop equation or node equation. But suppose it was not so. Suppose it was not so. Suppose it was more than 2 loops. Okay, more than 2 elements. Suppose there was a third element or a fourth element. Even then, one should not be disheartened because one can work with a ladder. You start with V2 and go back. You can find out the transfer function easily. Is this making sense what I am saying? This is what one should do. Yes, that is what one should do. Our last problem of the
Sir,
day.
here we have assumed that the reference level of V2 and Vg is same.
We have assumed what?
That the reference level of V2 and Vg is same.
Yes,
So can't it have been the case that when we are realizing the transfer
correct.
series capacitor and shunt inductor, there can be a resistor in the lower band.
There can be resistor here.
Yeah.
Well, I will bring it here. Well, in this loop, it doesn't matter where that resistance is put. This is the most favored type of circuit in which the input and output have a common ground. That solves many of the electromagnetic interference problems. So this is the type of network that we usually prefer. That's why we have chosen this. Okay. Our last problem of the day would be 1211. We will solve the most difficult one. E. 1211E. The problem is to synthesize the following function in the form shown in the figure. That is, we have to synthesize the given function in the form of an LC network terminated in a resistance of 1 ohm. Terminated in the resistance 1 ohm. See the next page, problem 1211, figure, problem 1211. This is the network given, and the function is y21 equal to S squared divided by S plus 2 whole to the 4th. Is perhaps the toughest of all this. So what we do is, first we write the denominator. Binomial expansion. We shall have S to the 4th plus 4S cubed. Can you guess what the next one would be? No. No. 4C2 multiplied by 2. So it will be 12 S squared. What is the next one? 16. That is correct. 4C3 multiplied by 2 squared. No, this is binomial. This is binomial. Why 8? 2. What is 4C2? No, 4C1
4C1 S cube
is 4. Oh, okay. You are right. I beg your pardon. I made a mistake. Is this okay now? No. 16S plus.
24S square.
Oh boy.
4S square 32S plus 64.
Is it that bad? 2 to the 4. Is this 32? Is this 32 all right?
Yes, sir. 32S plus 16.
What is 4C2? 12.
Yes, sir, 32 is already.
32 is all right. This 24? Oh no, we should not be stuck at such simple things. This is quite far from the network. 24S squared plus 32S plus 16. Now, so what should be our Y21? S squared divided by 8S cubed plus 32S. And Y22 should be equal to S to the 4th plus 24S squared plus 16 divided by 8S cubed plus 32S. Alright?
So Y60, we have to take out 1 and then.
Pardon me?
We have to take 1 out and then we have to divide.
We have taken 1 out. That is how we will get Y21 by Y22 plus 1. We are dividing the even part by the odd part. That is how we get 1 plus Y2. The point that I wish you to consider now is, where are the transmission zeros? There are 2 at the origin,
4 at infinity.
2 at infinity. At infinity it is of the form S squared by S to the 4th. So what should be the structure? Once we know the structure, then we will be able to get the network. 2 at the origin.
Captain, there are 4 transmission zeros and S equal to minus 2.
That's fine.
No, okay.
At S equal to minus 4 poles. Transmission zeros are 2 at the origin and 2 at infinity. Now 2 at the origin, mind you, we are developing Y22. So we start from this end. 2 at the origin, 1 can be an inductance in series, alright, and 1 can be a capacitance. Inductance in parallel, in shunt, and a capacitance in series. These two will take care of 2 transmission zeros at the origin. Then the question of infinity. What should we have here? A capacitor in shunt and an inductor in series. The last element is a series element because voltage source. This is V1 and this is a termination of 1 ohm, and this voltage, I am sorry, it is not the voltage, it is the current I2, that is our concern. Okay.
So why do we take these transmission zeros in the order of transmission zeros at origin and then at infinity?
Good question. Why you wanted me to take the infinity first?
Yes, sir.
Yes, we could do that. So we could have done this like this. This is also a perfectly valid. The element values shall be different. Then what? Then I should have an inductance and a capacitor. This is perfectly all right.
And also in the order of S is equal to 0, then S is equal to infinity, then S is equal to...
No, I didn't understand what you said.
So now can we...
One at S equal to 0, 1 at S. Yes, yes, yes.
We can do that.
Any structure which makes sense is perfectly all right. Now, question is, how do we develop this structure now? What you have to do is to develop Y22. Yeah.
If we had 3 zeros at the origin.
If we had 3 zeros at the origin, we would have another inductor here. Another inductor in shunt. And a
So that means two
pole.
inductors and capacitor battery.
Correct?
Then we could have two, instead of an inductor and a capacitor, can we have two inductors?
No, 2 inductors at the start. Here, there should not be, it should not be allowed because it's equivalent to 1 inductor. Okay? That you have to check.
No, so one in series and one in shunt.
You see, I could not have something like this, as I had discussed in the class. Why? Because this is equivalent to 1 inductor. If we take the Thevenin equivalent, it will be a constant multiplied by V1 plus 1 inductor. Any other question?
So can the capacitor and the inductor in series
Can the capacitor and the inductor be, which capacitor and which inductor? These two?
yes, sir.
Yes, they could be in series.
So can they be together, sir?
Can they be together? Yes, that's what I mean. They could be together, provided you could put the other one in proper positions.
No, so
But if they are together, they are equivalent to one capacitor.
Pardon me?
They are
No.
together in series.
If 2 capacitors are in series, that is equivalent to 1 capacitor. No, but I could have something like this. I could have something like this. That is not equivalent to 1 capacitor. Any other question before I say about the synthesis?
So this will come when we got one transmission 0 at S equal to infinity and then 2.
2 transmission 0 to at infinity, this, and 1 at the origin. Okay?
So
Yeah.
can it be like this? Then the first is capacitor in series, then inductor in series, then inductor in parallel and capacitor in parallel.
Correct? That can also be a perfectly valid structure, surely. Why not? This is also a perfectly valid structure. If there is one solution to a synthesis problem, there is an indefinite number of solutions. But of course, solutions have to be reasonable. I mean, they have to satisfy the original specs. Now, go back to this question, how do you develop Y22 now? Obviously, 2 steps of cover 2, then change over to 2 steps of cover 1, right? If you want to develop this, for example, then 2 steps of cover 1 followed by 2 steps of cover 2. You have to be very careful. There is a blind method also. You don't know cover, you don't know cover 1, cover 2. That's right. You continue to remove the poles. There is still another. Suppose you don't know how to remove poles, but you know network analysis. You give it to a first year student who has not done any synthesis so far. How will he do it? He will assume that this is L1, C1, C2, L2, blindly analyze this and then equate coefficients. One could also do that. That's a very lengthy procedure. Synthesis gives you a simpler tool. Okay, more tomorrow.